Morning. So I'll be presenting on the Washington State Fish Passage Program history and kind of an update, and then Dave's going to be presenting more on the design side. So a little history on our Fish Passage program. So prior to 1991, barriers were really just addressed as highway projects or maintenance projects impacted an existing barrier that they couldn't design around. And there was not a separate program. So after that, after 1991, the department actually developed a program. There was a small fund, which a lot of our programs have small funds. But we did have to have a priority of which barriers are to be corrected, and that's what we went to legislative for support on that. And we've kind of been working on that, you know, up until the 2013 injunction, which I'll go over in a little bit more detail. But our primary funding mechanisms during that time was still during state highway projects, because the funding was very, very low in just the program itself. So in 2013, there was a federal injunction where basically the Western Washington tribes sued the state of Washington because of the impact that the barriers were having on fish harvest. And the program wasn't really dynamic. Like I said, it was very small funding, and so they wanted an acceleration of the barrier corrections because of the impacts that it's been having on their harvest, and in turn impacted their treaty rights. So the injunction, just kind of a summary. I know a lot of you guys have probably heard about the injunction and recent appeal, which I'll get into that too in a little bit. But that's the area of the injunction boundary. So it was not statewide, it was Western Washington. However, our fish passage program is statewide, but the emphasis area, because of the injunction, is in the Western Washington state. So there's a lot of numbers up there, but so just in summary, so over 1,500 water crossings are subject in the injunction area. There's a lot more statewide, which I'll go into later. There's over 800 crossings that have significant habitat, or barriers that have significant habitat, which is greater than 200 meters of connection or potential habitat connection. Because of course there's going to be barriers upstream or downstream of ours. So we assume those barriers are gone in our assessment. So as far as what the injunction means to our program is approximately 475 barriers are required to reach a 90% of that habitat gain. 171 barriers having less than 200, they're still required to be replaced in that injunction timeline, but it can wait until we've been allowed to defer those replacements until the end of the useful life of that structure. And the definition of that is to be determined yet. So right now we're assessing that as when the culvert fails, then they'll be replaced with an appropriate size. But we are in the process of evaluating what the definition of end of useful life is. All that has to be completed by 2030. So whether or not you've heard that, so the state has tried to appeal with not necessarily the fish passage removal program itself, but the 2030 date was the primary appeal. So that didn't happen, and the 2030 date stays in place. So by 2030, we have approximately 475 culverts that we have to replace, and I'll get into a little bit more about that later. So as part of the program, we are partnered with our sister agency, which is Washington State Department of Fish and Wildlife. And their role is really to do the statewide barrier inventory. So annually they go out and do inventory on all of the crossings statewide. So there's over 7,000 water crossings along the state highways. Over half of those have been identified as barriers. So it's a very dynamic program because, again, they go out and assess it annually. So there's full barriers. I don't know if you, so the green are corrections, so the barriers that we've corrected. Red dots are total barriers, and yellow or orange dots are partial barriers. That's the dynamic part, because in one year it could be a barrier, the next year it may not be a barrier, or something that was not a barrier could be a barrier. It all depends on how the flashiness of the system. So that's why it's a dynamic. And as far as the injunction is concerned, if it's within that boundary, a barrier is a barrier, whether it's full or partial, that part doesn't matter. It's an online database, so it's the public can access it. We use it as a huge communication tool between the tribes and DFW and all our resource agencies, just to show our progress as we're going through. It also helps us with our prioritization of our program as we're trying to do, you know, bundled projects, because we may have one project that may have like 5 culverts in it, and as I'll talk about later, we're going to see more and more of that in order to meet this 2030 deadline. So I've actually broke this table up into some other slides later on, and I like pictures, so I'm going to move to the pictures instead. So that's a statewide. Those are all the barriers statewide that I just talked about. The blue is the injunction boundary, so you can see that's where the heavily populated barriers are because of the Puget Sound area. So to date, since we've been correcting barriers, again, that's prior to 1991, so we've had 319 fish passage projects, or fish passage projects statewide as of last year. We corrected 330 barriers, because like I said, a project may have multiple barriers in it. And we've corrected over 1,000 miles of habitat gain. So we are moving in the right direction. The acceleration part, so since the injunction, that's really where we've kind of accelerated our program. So you can see in 2017, we've corrected 14 barriers. 11 of those were in the injunction, because like I said, the program is statewide, so it's not like we're forgetting about the rest of the state. We are still including those, and I'll talk about how those get programmed later. We've corrected, in just that one season, we corrected 45 miles of potential habitat. This year, and some of the projects go into multiple seasons, but we had 16 barrier corrections, 11 were in the injunction, and we corrected 100 miles of potential habitat. So you can see our program, in 2013, when the injunction happened, was about that 11, 10 projects a year is what we were trying to budget towards, which is what we were trying to go with the appeal. So because the appeal didn't go anywhere, the 2030 date still stays. You can do the math and realize that we're going to have to probably increase our effort by 5 times. So the current sources of funding right now, of course, emergency funds, like I said, those failing culverts. The state improvement programs, so if there's a project going through adding lanes or doing safety improvements or whatnot, and they do include a barrier within the project limits, they are now required to replace that barrier or correct that barrier. We're looking at a preservation, or the fish passage program is actually part of a preservation program, so that's kind of where that lives. And then any transportation projects or packages like the Connecting Washington programs, those will all include fish passage barrier corrections. We also have grants. A lot of the rest of the state of Washington gets funding through grants to replace theirs, because our emphasis is on the injunction area right now. So prior to the appeal, the recent appeal, our program was based on from 2005 to 2013, which is when that injunction happened. We were about $27 million is what we've spent in the program. After the injunction, we ramped that up to about $70 million, and that was kind of our plan forward. Because the appeal failed and said you will still have that 2030 date, you can see we still have $2.4 billion of fish passage program to complete, and in order to do that by 2030, we'd be, like I said, about 5 times the effort of what we're doing now. So we'd have to probably do 50 culverts a year And as far as I'm concerned, and that I've been told, that's what we're going to try to plan for. So we are moving towards that effort as of very recent. So that's it on my presentation. So Dave's going to go into more of the design details and then a specific project.
Thanks, Julie. As Julie mentioned, I'm going to dive into the design side of the fish passage program. We're going to talk about the design regulations, design criteria, and the design approaches we're taking at each of these crossings. But before we dive into that, I wanted to take a quick step back and talk about what is a fish passage barrier. Simply put, a barrier is anything that hinders any life stage of fish from moving through a waterway. And there's a variety of different types of barriers. As you can see, the main ones here are listed. A velocity barrier: if we have excessive velocities, fish can't pass. Depth, that refers to a minimum depth. Typically, if you have a depth of less than 0.8 feet, you're hindering movement. Water surface drop is related to weirs and grade control structures. So if you have a drop in water surface elevation of, generally speaking, over 0.8 feet, then you'll have a barrier. Excessive slope: if your structure or channel is too steep, you're typically going to run into faster velocities and shallower depths. The last type of barrier is obviously a structure. These can be tide gates, floodgates, or a dam. This graphic here on the right, if I can get this here, prevents a good indication of, this is for the entire range of fish livelihood. So it's not just for adults, it's also for juveniles. So we do have to think about younger life stages. Next up is the regulations. Regulations for fish passage design in Washington State are defined in the Washington Administrative Code. That's locally referred to as the WAC. The guidelines we follow, the document shown here is a 2013 Water Crossing Design Guidelines. It's authored by WDFW. It is the primary document that we follow when we're doing the design. Other documents that we use are DOT has a hydraulics manual. Chapter 10 talks about large woody material design. That specifies and defines what a key piece of large woody material is and how many pieces should be placed in each project. Other references include U.S. Forest Service has a good stream simulation manual, and HEC 18 for our scour calculations. Now, the overall approach to fish passage in Washington State is to take a geomorphic approach. And the intent there is to minimize the effect of the proposed structure and the proposed project on the natural processes that are occurring in the channel. So we don't want to create excessive velocities. We don't want to cause backwater impacts. I've listed 4 main approaches here. You can see stream simulation, bridge design, and hydraulic design. So I'm going to go into each of these in greater detail. Stream simulation is typically applied to smaller crossings with a bankful width of less than 15 feet. And you do need to locate a reference reach to use in your simulation. Bridge design is for crossings with a bankful width of over 15 feet. We're typically looking at confined and unconfined settings. And then lastly, hydraulic design, which is not really used, but I did want to mention here. Hydraulic design approach is applied for structures such as ladders, weirs, and also roughened channels and other drop structures. When we're talking hydraulic design, the design criteria you're looking for is velocities and water depths. So as part of collecting or following a geomorphic design approach, we need to collect geomorphic data. So before we start any project, we go out in the field with a large team of people. We go out there with the H&H folks, we go out there with the project design engineers, the stakeholders, which are in this case it would be WDFW, who is issuing the permit, and also the tribal entities who can provide comments during the design. Some of the pieces of information we collect, the most important is the bank full width. This is the most important parameter in stream simulation design. And it's imperative that at the beginning of the project, we reach consensus in the field with the stakeholders present. So we want to get an agreement on what that value is before we leave the site that day. Other pieces of information we need to collect are the longitudinal profile. This is typically, we get this information from a detailed topographic survey. WSDOT in general collects survey 300 feet upstream and downstream of the crossing, and then we supplement with LiDAR as needed. In other cases, we also will go out and just take just a longitudinal profile to supplement the detailed topographic surface. We're also collecting information on the channel substrate. So we'll go out there with a gravel meter, which you can see in the picture here, and collect pebble counts up and down the reach, and then come up with an existing gradation of the material that's present on the site. While we're walking up and down the channel, we take notes about the channel shape and pattern. It's important to know what the existing channel looks like so we can mimic it and understand, what our proposed section should look like. Also, while we're walking through the site, it's a good idea to notice and take notes about what size and what density of large woody material is present. Is the site showing opportunity and potential to move that large woody material? How big is that material? How often is it occurring? And then the last thing we collect while we're in the field are any constraints. And constraints can simply be private property. They can be existing infrastructure. For these crossings, it's common to see county culverts or county fish ladders immediately upstream or downstream of our crossings. One other thing I wanted to mention on the channel substrate is we found out also it's a good idea to take notes regarding the largest size material you're seeing in the channel. That may not necessarily be captured in your pebble count, but when we see bigger boulders, we like to at least take pictures and measure them. So now I'm going to jump into the approaches real quick. Stream simulation approach. As I previously mentioned, it's suitable for sites with a bank full width of less than 15 feet. These systems are typically moderately confined. The structure size is the minimum opening is size with this equation that has been established by WDFW, and it simply is 1.2 times your bank full width, and then you add 2 feet and round up to the nearest foot. That gives you your minimum stream simulation opening. This size is also the minimum size we will use for a bridge design approach, which I'll talk about on the next slide. When you're doing a stream simulation approach, your proposed channel and culvert should be at a slope no greater than 25% of your natural upstream slope. Stream simulation culverts are also countersunk 30 to 50% of their rise, which provides for a natural channel bottom. Freeboard on stream simulation culverts varies from 1 to 2 feet and depends on your bank full width. The bridge design approach is typically used for bank full widths of greater than 15 feet. It can be, there's two sub-approaches here. You can have a confined bridge or an unconfined bridge. And that's dictated by what is called the floodplain utilization ratio. It's also called the entrenchment ratio. That's determined by taking your 100-year top width, dividing it by your bank full width. If you get a value less than 3, you're considered confined. If you're greater than 3, you're in an unconfined setting. The structure size, when we're looking at doing a confined bridge, we just apply a factor of safety. So first off, we say, okay, here's the minimum opening by stream simulation, and then we increase it based on a factor of safety. Factor of safety should account for uncertainties in your hydrology, hydraulic model, and also for potential channel migration or aggradation. If you're doing an unconfined bridge, so your floodplain utilization ratio is greater than 3, you need to take into account, you need to compare the natural channel velocities to the channel velocities under your proposed structure. WDFW likes to see that be within 10%, so that ratio should be 0.9 to 1.1. Freeboard for bridges is obviously greater. It's 3 feet for bridges when compared to stream simulation. And the freeboard is what is necessary for to pass large woody material. The typical H&H analysis we do on these crossings, modeling obviously, We typically model existing conditions, proposed conditions, and then sometimes a natural conditions, which is a version of the existing conditions model with the existing structure and roadway embankment removed. Previously, we've been doing a lot of these models with 1D HEC-RAS. Now the crossings are being done in SRH 2D. The results from the modeling are used in the scour analysis, sizing the proposed streambed material, habitat design, and then also showing compliance for design criteria. For hydrology, we're using gauge data when available. Otherwise, USGS has recently updated in 2016 the statewide regression equations. Other times we'll use available studies, such as a flood insurance study. And then and climate change could be a whole presentation on its own, but I wanted to mention it here that for a site that has been identified as vulnerable for climate change, we're actually using the 500-year event to do the design. And then one other point I didn't make on here is right now, for some of our bankful calculations, we're using the 2-year return period flow for those calculations. I wanted to touch briefly on proposed streambed material. There's 2 ways where we're essentially designing and specifying the material for our proposed site. The first is simply match what's there already. So go back to our pebble count and come up with a gradation that is close to what's out there. And this is typically for systems that are in equilibrium and we don't have a sediment supply problem. For sites where we want to see some stability or more increased stability, what we'll do is actually look at incipient motion calculations or a unit discharge method, and we'll size our D84 size particle to be stable during the 100-year event. Specifying proposed streambed material, what we typically do is percent by volume, and to make it easy on the contractors, we're using standard washout items, so streambed sediment, cobbles, and boulders. And we'll say 30% streambed sediment, 70% cobbles. Contractor will just take those scoops on site, mix them up, and then put them in the stream. So now that I blew through the design methodology and approaches, here's just a quick example. This is Fisher Creek. It's a confined bridge. It is just north of Seattle on Interstate 5. It's about 50 miles north. The existing bankful width we determined on site and through hydraulic modeling was 24 feet. The existing culvert was an 8-foot CMP and it was retrofitted with baffles. Again, this is a confined system which was verified by the site visit and hydraulic modeling. It had a floodplain utilization less than 3. The constraints in this crossing are immediately upstream is a county fishway and a box culvert. The proposed design, we ended up with a 30-foot minimum section. That was based on a factor of safety of 1.25. The other features in the project included a roughened channel to transition from our section to the existing fish ladder. And then we also included habitat features, which included large woody material and boulder clusters. So this is just a better picture. On the left, you can see we're looking downstream from the top of the fish ladder. That dark area in the background is the 8-foot CMP. Then on the right, you can see that the section has been dramatically changed and increased. This is just a proposed plan, which is hard to see. The only thing I wanted to point out here is that here's the bridges, and here's some large woody material. Currently, WSDOT is not placing large woody material and habitat structures underneath bridges or within 50 feet. Here's a proposed section. This was just based on the section identified in our reference reach. Just another picture from construction, looking downstream, and then also looking upstream. So, with that, I wanted to jump over to lessons learned to wrap up the presentation. This is specific to Fisher Creek, but Julie's also going to interject and talk about some of the others on other crossings. This first bullet point, we came up with a bankful or a proposed opening of 30 feet. This was less than the stream simulation equation, and that resulted in, one, us deciding to use the stream simulation as our minimum opening width, even for bridge designs. But really what it meant was additional coordination with stakeholders, alternative analysis, and hydraulic modeling, which impacted schedule and resources. In this crossing, at the very end of the crossing, we had a late stakeholder comment, and they wanted to see a low flow channel grading to connect habitat features. So if I go back a slide, you can see this nice channel was connected. that didn't stay there too long. And we weren't surprised by that, but I think some of the stakeholders were looking for that to be a little more durable. Stream restoration is the long-term process. I think we have to manage expectations and that it will take time, but it will get there.
So we are out of time, so no questions. But if anybody wants to meet with Dave or I throughout the conference, we will have no problem having conversations. So sorry about going over.